So hello everyone, my name is Lucas Ferreira. I'm a professor here at the Departamento de Informática, and this is INF721, Deep Learning. This is our first lecture, and I'm going to give you a brief introduction to this topic. Okay, so for our first lecture, this is just a brief introduction. I'm going to go over I'm going to talk a little bit about me, but also I want to hear from you, a little bit from you, why you're here in this course. Then we're going to move to an introduction of deep learning per se, and I'm going to give you the overall syllabus, including the logistics of the course, exams, how you're going to be evaluated, schedule, communication policies, and whatnot. And then I'm going to already start a little bit of content here. We're going to go slowly today. I'm going to talk about machine learning and the main problems of machine learning. We're not going to see any neural networks today, but starting from tomorrow, not tomorrow, on Wednesday, we're going to start actually looking at our first models that are going to be foundational for neural networks. Okay. So a little bit about me. As I said, my name is Lucas, and before coming to Viçosa, I was a postdoc at the University of Alberta in Canada as part of AMI, which is an institute there. And I did my PhD in computer science at the University of California in Santa Cruz. And research-wise, I'm interested in the intersections of artificial intelligence and creativity. Particularly, I work in the problems, at least currently, I've been working in the problems of music generation, procedural content generation for games, and game AI. So if you want to contact me, my office is at the CCE 401B, which is in the same floor here. And my email is that one, lucas.n.ferreira@ufv.br. Okay, so I want to quickly hear it from you, and this is also like a moment for us to break the ice, just and start speaking. Again, don't be shy. If you don't know what to say, here is a script. You can say my name is, and then say your name. I'm a first, second, third, whatever year you are, undergrad, master's, PhD student in computer science, physics, whatever major or course you're doing. And then just a few words about why you're taking this course. I'm taking this course because, and who wants to start? All right. Okay, guys, yeah, C doesn't hurt, right? Well, so I'm really excited. There's a wide range of background, which is cool. And yeah, for those of you who are here because you need to take English courses, yeah, welcome. For those of you who are undergrads who are willing to, or who wants to just dig deeper and start learning about neural networks, also this is going to be a good place for you. And for those of you who already actually have been working with machine learning and neural nets, this is also a good place. I hope you guys can learn a little bit more throughout the course, okay? So I want to get started from the basics. We are almost all of us here are computer science students, so I actually started motivating neural networks from the computer science perspective. And I'd like to state that we all know here that algorithms are normally or traditionally implemented as concrete functions, right? We have a function named f, and you have an input x, and this function f maps somehow the input x to the output y, right? This is very basic, and I want to illustrate so we can go very slowly here, right? Let's think of a problem. This is a problem 1. It's just doubling a number, right? So we would have a function like this. F of 8 would be equals to 16, right? And f of 24 is equals to 48, right? This is just an example. We all know how to solve this problem. We can just write a simple function that is f of x equals to 2 times x, right? This is pretty easy, right? Nothing really fancy here. We can get a little bit more complicated, right? Let's think of this problem now, problem 2. And this is the shortest path between 2 points, right? Let's think of this example. Imagine I want a route from Viçosa to Belo Horizonte. So our function f has as an input 2 arguments, location A, which is Viçosa here, and location B, which is Belo Horizonte, right? So we would like, with this function, to get the shortest path, or the shortest route from Viçosa to Belo Horizonte, which could be, for instance, Viçosa, Teixeiras, Ponte Nova, Ouro Preto, and Belo Horizonte, right? This is not such or as an easy problem as the other one, right? But we know how to solve it, right? And we have a few algorithms that we know that could solve this problem. For example, Dijkstra's algorithm, Bellman-Ford, and Floyd-Warshall, okay? But now let's think of an even harder problem. We want to write a function that takes as input an image and outputs a label. For example, let's think of even a simple instance of this problem, which is you have images of cats and dogs, and you have to write a function that gives the output cat if the image is a cat, or dog if the image is a dog, right? Does anybody know how to write such a function? Well, it's tricky, right? First of all, our input is an image, so it's a 2D array of pixels. And we would have to somehow find a formal description of what a cat looks like and what a dog looks like. But there are many dogs and there are many cats, right? And the pictures themselves could be different. You could have the same dog from different angles and different sources of light affecting the image, and all of that would give you a different distribution of pixels. So how could you write such a function if there are so many exceptions and so many rules, right? So it's very hard. And in fact, people have tried to solve this problem for many, many years, and in this, trying to find these rules to answer these similar questions to this, right? This is just a toy example, but reflects a lot the kind of problems you're interested at, or in, sorry. So yeah, it is not that easy anymore to write such a function, okay? But how can you solve these problems? And this is when machine learning comes in. So machine learning is a set of techniques, right, that we can use in computer science to find a function from experience, or say we call experience here data, to perform a particular task. And the task here would be, for example, classifying images or all sorts of other tasks, right? So the field of machine learning is interested in that. How can you write programs that we don't have to encode rules inside these programs, but even without these rules, they can solve such problems, right? And neural networks are just one type of method inside the field of machine learning. So it's one kind of algorithm, let's say, that we have in traditional machine learning that we can use to learn functions. And, well, let's see how neural networks work visually, at least. So we could visualize our space of points or data. Let's call these dots on the screen data points. And we have red data points and green data points. Here, I'm just simplifying the problem, showing that the red data points are images of cats, and the green data points are images of dogs, okay? Obviously, this is not a two-dimensional space, right? It's much more complicated than that. But I'm just so we can visualize, I'm plotting this in 2D. Well, we could build a neural network, and we're going to talk about this throughout the whole course. We could build a neural network that takes as input an image and outputs a prediction of the label of that image. Don't worry about what this really, like the actual circle here means. We're going to call it a neuron very soon, but it can, and we will see this also probably in the next lecture, that this kind of neuron, or we can call this a unit in the context of neural networks, can represent a line. Or in other words, more formally, we could say that this neuron could represent a linear function, right? And our goal here, I didn't say this before, but our goal here in this case, which we call a classification problem, is to find a line that separates the green dots from the red dots, okay? But, well, there isn't a line that separates these two classes of examples, right? But with a single neuron, that's the only thing we can do, okay? That's what motivates the idea of layers, or combining these neurons together in this kind of layered structure so we could represent more complicated functions. Okay, so now you can see that such a neural network with 3 layers, we will see this, it has like 1, 2, and 3 layers. It has also an image as an input, and it also gives a prediction, which is a label. But now, because it has many neurons in that structure, it can represent more complicated functions. And in the deep learning literature, or in the machine learning literature, we call such networks shallow networks because they have few layers. So in this case, we have this first network here on top has just 1 single layer. This one here has 3 layers. Traditionally, up to 3 layers, we consider these networks shallow. But up to some point, then we start calling them deep neural nets because they have many, many layers. I'm just showing 4 here, but they can have many, many, many more, okay? So what is cool about these deep neural nets is that they can represent really complicated functions. And then, depending on how you combine and create these layers, you can actually find a nice curve that separates that, those two classes. We will see that it's a little bit different than this, but the intuition is that, okay? I hope you get the intuition from these images. Any questions? Okay. So why should we study neural networks other than we know this is what runs underneath ChatGPT and all these kind of cool technologies these days, right? Here is some information about how well they work. So let's think of a plot where on the x-axis we have a data set size, and on the y-axis we have performance. Don't worry how performance is measured right now. Just think of that, how good the model is on the y-axis and the size of the data set on the x-axis. So what researchers have done is they have evaluated different models in different data scenarios or data set regimes. If we consider classic algorithms like logistic regression, which we will actually see next lecture, decision trees, SVMs, and other algorithms, which we normally study in machine learning courses, what happens is, as the size of the data set grows, they kind of converge on performance. So they stop getting better. Right? And what we see with neural networks is actually the opposite. If you train small neural networks, you're going to get that kind of curve. So they will get a little bit better. If you increase the size and have medium neural networks, the performance is going to grow. And the same with large neural networks. So these results are still being actually evaluated, because if you think about the current AI paradigm, we are still trying to increase the size of our neural networks. So in the last couple of years, what you've seen like from big tech companies like Google, OpenAI, DeepMind, they are just making bigger and bigger models and getting more and more and more data. And the neural networks are actually still getting better. So we don't know when they're going to converge. So this approach is very, very similar to what we had in the processing run, or the processors run in the 90s, where Intel and AMD, they were just making smaller and smaller and smaller chips, because that would work, right? If you make your chips smaller, they would become faster and faster and faster until they reach a convergence point which was, I think, at Intel Pentium 4, which they couldn't get smaller than that because it would just it would heat up so much that the cooling system would just become just too expensive. So here we are seeing some sort of race like that one. Companies are just making bigger and bigger and bigger networks and just getting more data. And this is still like getting us more performance. We don't know when this is going to converge. Some people say it's going to be very soon. Some people say, no, it's still there is maybe a decade of that, right? Which, I don't know, my opinion is ChatGPT is already being trained on almost the entire internet. So I don't know from where they're going to get more data. Really, I don't know. So there's also like one disclaimer here is that it's not only quantity, it's also quality of data. So there is a limit, we just don't know yet. And this is just like a cheaper, maybe not cheaper, but easier approach for companies because you can just keep trying, right? You just put more money and you get more results. Okay. But there's a reason for this, right? Like this performance or these models didn't came up all of the blue. So, and also the whole context of the society as a whole actually, and science and technology allowed these things to happen. If you think about the last 20 years, right, the internet as a whole grew like considerably. The whole society became more digital with mobile phones and like all the processes now are all digital. We don't write stuff on paper anymore. So suddenly we have access to digital data very easily. Imagine like 20 years ago, a machine learning researcher actually had to go and put the data in the computer because the data itself wasn't actually in digital version. And now everything almost automatically is stored in a computer somewhere, right? So we have access to data and large quantities of data, which wasn't true like 20 years ago. We also had a kind of a revolution in especially in neural networks, where some researchers invested quite some time trying to make these models work on GPUs, or graphical processing units. This is quite a recent advance. I think like in the middle of the last decade, this became kind of like a popular thing to do. But before that, also maybe before 2015 or something, it wasn't common to train neural networks on GPUs, and this was a big part of it because it made much faster to train these models and also to run them. On top of that, we have now very cool and easy to work frameworks like PyTorch, and we had TensorFlow before and others that makes it much easier to program these things because now we don't need to do auto derivation. Actually, sorry, we don't need to compute the gradients by hand. We're going to see what this means in the next couple of lectures. But neural networks are trained with an algorithm called gradient descent. And to run that algorithm, you need to compute the gradients or the derivatives, or the partial derivatives of the neural network with respect to some loss function. And that used to be very complicated back in the day because you had to do that by hand yourself, and that was very slow actually. First of all, you needed a very strong calculus background, and and that on its own limited a lot of computer programs programmers to actually use deep learning. And now it's actually much easier because these things are done automatically for you. And obviously there were a whole new era of algorithms within the context of neural nets. We're going to see most of them. If you look at the last, again, 10 to 15 years, there was a lot of advances in algorithms for neural networks, both for training and inference. Oh, okay. What is interesting here is that if you take a look at this portion of the graph, which is where the data sets are very small, right? Actually, most likely, it's not very fair how it's drawn here, but normally in these low data regimes, the classic algorithms work much better than neural networks. So this is what I'm trying to say here. So neural networks really stand out on large data set regimes. Okay, so, and it's important to say that because nowadays people think neural networks are just silver bullets, you can shoot at anything. But no, there's still room for this from these algorithms here, especially when you have a very small data set. Question?
When you say like small data sets, you mean like how small?
Yeah, this is a very tricky question. There isn't a number, right, you can put, but because, for example, if you're working with medical images, you might have 10 images, right, or 15 images, because if you're running an MIR, for example, that is very costly, right? So you won't have anything bigger than 100 is really large, right? But if you're working with images of cats and dogs, then that's actually, you should just Google them, you're going to get millions of them, right? So it really depends on the problem. But what we have, and we can discuss this later, is, for example, if you're working with images and you're trying to use neural nets, we have cool results from other problems that you can try to generalize. For example, oh, I'm working with image classification for animals. And then most likely there's going to be a paper and on that problem. And then you can see, oh, we tried to use 10,000 of images, we got this accuracy. We increased a little bit more, and then we got that. So if your problem is similar to this problem, then you can kind of guess based on what previous experience had told us. And yeah, I think this is the best way to go, is try to approximate to some other problem in the literature and see if they already have a good number for you to base on. Because again, think about this. Even if the big tech companies or the big research labs, they don't know the limit yet. So they don't know how large is large, right? So you have to try. The problem is sometimes here, honestly, we don't have enough money to do that, right? So it's tricky. It's really tricky to know how much to invest on getting more data or just trying other algorithms. It really depends on the scope of your project. Okay, so all of that being said, I hope you are motivated to study neural networks. And what I can offer to you in this course is, formally, this course introduces you, students, to the fundamentals of and modern techniques of deep learning, aiming at enabling you, students, to design and implement deep neural networks for classification, regression, and generation of unstructured data. This is important because, again, I didn't say that in the previous slide, but neural networks also excel a lot on unstructured data. What do I mean by that? I'm talking about data such as images, text, audio, all these things that we cannot put in a table. Right? When there's a data that we can fit in a table, let's say if you're doing house price prediction, or if you have an Excel sheet with numbers in there, we call these structured data because they are nicely put in a table, right? You have columns, and you can select the columns, and this is from where the structured word comes here. Obviously, you can apply neural nets to structured data, but these kind of problems have already been studied a lot, and here we are more interested in the modern, more recent problems. Okay, content. We're gonna start the course probably the first 3 or 4 weeks. We're gonna talk about the basics of neural networks, and this includes what is machine learning, like the basic linear models, the gradient descent algorithm, which is the main algorithm we use to train neural networks, and then these kind of models right here, which we call multi-layer perceptrons, which are networks that process the input just in one direction from the left to the right. Then we're going to see the backpropagation algorithm, which is the algorithm we use to train this kind of networks. So gradient descent and backpropagation, they kind of walk together. The backpropagation part is just a very, it's a nice way of propagating the gradients back from the output layers to the input layers. And it's an efficient algorithm to do that. And throughout, sorry, question?
Sorry, I have a question
Yeah.
about the final work. Do we have to implement it using NumPy, or can we use PyTorch or TensorFlow?
You see, I'm going to talk about that. Yeah, don't worry. You're gonna use PyTorch. Don't worry.
Okay.
But for this very first moments of the course or module, if you will, we're going to actually implement everything from scratch using NumPy, which I think is a very cool and important experience to have, especially if you want to be a researcher in deep learning. You have to do this at least once in your life. And obviously, I'm going to be here to guide you. The assignments are going to be guided. And we're going to actually derivate these things by hand in class. And as you see, it's not going to be as complicated probably as you think. So don't worry. And this kind of things I don't actually put in exams because I think this, like doing this math, it's nice to do it once, but you don't have to actually do this every day. So it's not a kind of experience that is extremely important to be fast at. You have to know how to do it, but you don't need to do it fast these days anymore. At least that's what I think. Oops. Oh, sorry, the animations are actually in the wrong order. Okay, so after that module, we're going to see a couple of techniques to improve neural network performance. Namely, you'll see regularization, normalization, some advanced optimization algorithms such as ADAM, which is kind of a new version of gradient descent, with some momentum that can help you kind of getting away of local minima points when you're actually optimizing your neural network. Then we're going to see some ideas about how to tune your hyperparameters with some search techniques like grid search. And this is the thing that I always wanted to talk about, which is how these frameworks actually do automatic derivations. Not sure we're going to have time for that, but I really wanted to include that somewhere in the course, which is very cool. Well, the third part is actually the more fancy neural network architectures we normally use these days, which are the convolutional neural networks, or CNNs, that we normally use to solve problems related to images. Then recurrent neural networks that we normally use in the context of natural language processing, or NLP, dealing with text problems, or any kind of language problems, including language models, which is very popular these days. Then perhaps the most important architecture right now, which is the transformer, which is what ChatGPT uses underneath. Then we're going to see some case studies of all these networks move to transfer learning, which is this idea of learning to solve one task and then try to use that knowledge you have, or the network has, to solve another problem. So how can you explore or exploit ideas that you have learned before to solve a second problem? And then implementação. Forgot to translate this. And then PyTorch implementation, which is, we're gonna, at this point, we all would have done some. So in the first part, you guys will do the derivation by hand, but then it's done, right? I want you to do it once, and then once you do that, you can start using PyTorch for getting to harder problems. Because actually, if you spend time doing the derivation by hand, it would take even more time, and then you wouldn't get to the cool hard problems, okay? So from that point on, it's fine. And we're going to see some PyTorch in the lectures. We don't have labs in this course, so we don't go and have spent like a lecture there talking about how to implement these things. But I try to bring as much as I can some notebooks and discuss some practical implementation details with you. Okay. All right. And then at the very last weeks, we're going to talk about one of my favorite topics, which is generative AI, which is very popular also these days, which is how to learn to generate data instead of classify or run regression, for example. So my research mainly focuses on generative AI, and I spent 5 years of my PhD working with these models, including the moment where the transformers came in, and then I had to deal with that in the middle of the process. But you're going to see how generative adversarial networks work, like or GANs. We're going to talk about autoregressive models, which is like transformers and how recurrent neural networks can be used to generate sequences. Also variational autoencoders and diffusion models, which is very popular to generate images these days. Oh, by the way, I forgot to translate this, but this image I've been using, and the cat one as well, has been generated by Midjourney, which is a diffusion model. And you can't see very much. Can you turn off the light, please? Yeah, so here there's a lot of cool background that it's hard to see, but the caption says a realistic photo of a dog sleeping on the couch of an apartment, books and plants at the back. So with this single prompt, the Midjourney generated this high quality image. And the cat one is the same thing, but with a cat instead of a dog. Okay, I guess you can turn it on. Okay, prerequisites. This is important. We have a mixed background here, but I'm going to assume that you have a background on data structures, because we don't have time here to cover the basics, right? And by the basics here, I mean some Python programming. And if you're not familiar with Python, it's fine, but you have to be familiar with at least one programming language. I'm sure Python is simple enough that you can learn on the go if you already know another programming language. But if you haven't programmed before, this is going to be very challenging, okay? And what I meant by data structures is just basic linear and non-linear data structures like trees and lists and stacks and their associated algorithms, okay? We're going to use a lot, but basic stuff from linear algebra, mostly basic operations with vectors and matrices. What I say when I say a lot is just these things are going to show up probably every lecture, but the extent you have to know is pretty much how to multiply vectors with vectors, vectors with matrices, what is a dot product, and whatever is more complicated than that, probably I'm going to review during the lecture. So, but I need you to be familiar already with these things, because we don't have time to just like start from scratch. And calculus, I put calculus 1, but I think it's 2, to be honest, because we need to deal with, we're going to deal with multivariate functions. And we're going to have to actually be able to compute derivatives. And there is one special lecture where this concept is very important, and which is the lecture about gradient descent. And when we come to that, I'm going to make sure to review what a derivative is and how to calculate the basics, some of the basic rules. We don't have to remember them by heart. I actually myself don't memorize all of them. So I'm going to review the things that are important, and then we're going to do the derivations very slowly, and I'm sure it's going to be fine. Okay. Well, now it comes to the important part, which is grading. You all are going to be evaluated according to 3 major activities. We're going to have exams, which comes to 40% of the grade. Programming assignments, which are my favorite part, 40%. And there's a final project, which is 20%. Okay. Last time I thought this, I had quizzes, but they ended up taking too much time of the lecture, and we had to go to the lab, and so we needed a second room. It was very messy, so I prefer to do now exams here in the classroom, and then we separate once, like 2 days for that. There's going to be 2 exams. So we call them midterms because they're going to be in the middle of the semester. There's not going to be a final exam in the sense that the last week doesn't have any exams. And they take the entire classroom time, but normally they're designed to take less time than that. Most likely, there's going to be a mix of objective questions and some more open questions where you have to discuss something. But I'm not a very harsh professor in terms of exams, so don't worry too much about this. Important logistic thing here, if you have to make up an exam or if you can't attend the exams on the scheduled dates, please let me know in advance so we can schedule a time for you. So the programming assignments, you're going to have 4 of them. And these are going to be in Python, written in Jupyter Notebook. You can think of this as a Google Colab file that I sent to you, and you just complete it. They're designed to take 1.5 weeks. Actually, you can do it in hours. To be honest, if you sit down to work on the assignment, you probably can solve it in a few hours. But since you're taking more than 1 course, and you are also, some of you are actually seeing this for the first time, I hope there's enough time for all of you to address and solve the assignments. So we start with logistic regression. Question? No.
Yes. Just to be sure, these are individuals as well, right?
Yes, they are.
Okay. Thanks.
So first of all, it's going to be logistic regression. Here we're going to do everything in NumPy. But it's very guided. So there's even test cases for you to actually check your work. So if you get to the end and all the cells are working, you are done and you can go work on something else. And you know you got an A grade or 10. Second one is MLPs, and also they're going to be implemented in NumPy. This is a little bit more complicated, but again, I think with the guide there, with the tutorial style type of thing, it makes it work, or it makes it easier for all of you to solve that. And then from the P3 and P4, we're going to implement in PyTorch. So I think there's a nice balance here between working kind of from scratch in NumPy and then working with more modern frameworks at the end. And my idea here was to give you an experience on all of the major neural network algorithms. Of course, logistic regression is not officially a neural network algorithm, but you can see a logistic regression as a neural network, as we will discuss next lecture. Okay, late policy. If you don't finish the assignments in time, you're going to lose 15% of the total grade per day that you are late, and you can be only 2 days late of maximum. Okay, if you don't turn your assignment in 2 days, then you miss the opportunity. Then you can't turn it in anymore. Okay, so the idea here is because we're going to have things coming up on one after the other, so I don't want you to be late on something and then miss on the next one. So it's going to generate kind of a snowball effect that I don't want that to happen. Okay. And the final project is, well, it's a quote-unquote research project you guys are going to have to do. And this is a new thing I'm introducing in this course, not the final project, but how it's going to be structured. So it has three parts. So we're going to propose what you're going to do first, which means you're going to find a paper that is related to your work or not, whatever you want, but it has to be a paper using transformers. And I'm limiting this because, first of all, this is the most important network these days. And some people might say, well, I'm not actually going to use transformers in my research. Well, I'm sorry, but eventually you're going to have to deal with this. And I think that transformers are complicated enough that if you understand them, you're going to be able to do any type of network that you want. So I think that you might say, like, yeah, I'm going to actually waste time. No, it's not going to be a waste of time. Trust me. Transformers are everywhere. They are in vision problems, they are in text problems, they are in simple classification problems, machine translation. There's application to pretty much anything you can think of. And if there isn't an application of transformers that you want to investigate, there's probably a good idea for a paper. Okay, so I'm going to try this for the first time. And I hope most of you are actually aligned with this in your research. But the idea is that you're going to have to reproduce that paper. By reproducing, I mean you're going to have to read it, understand it, and re-implement the paper using PyTorch. And then the idea is that, so most of the papers nowadays, at least in computer science, they have a GitHub associated, so you can actually get the code from the authors. But normally the code itself is very messy, is very unorganized, and hard to read because those are research code. It's not actually commercial code. So, and we as researchers have to do that all the time. You have to go to a GitHub repo, find where things are, and then understand from the paper where that thing that is said on the paper is actually on the code. So then actually figuring that out and transcribing that text to a more clean code that you actually understand. That's very important. And my suggestion here is to find a paper that can be a baseline for your research, because that actually helps then directly moving forward. But again, another argument for focusing on transformer is that we don't have time to have an assignment for, let's say, I could have a programming assignment on transformers, but that then would leave us with 2 weeks for a final project only. So I decided to not have an assignment for transformers and then make it the final project a transformer project and give you 1 month to work on that. Okay? So you're going to have four weeks to implement this. And I hope this is going to be a really cool experience. Okay, speaking of schedule, this is my initial organization. Most likely things are going to shift and change a little bit, but this is my plan. We are here, first row. Today is the 9th. We have the introduction lecture. Then next Wednesday, we're going to see the linear models. And then we move to gradient descent. So up to here, actually up to here, third week, we have the first module, as I said, which is the basics. And then this weeks 4 and 5, we have this advanced or optimization algorithms and stuff to help improve neural networks performance. And then we have our first exam at the end of week 5, which is exactly a month from now. And then we start looking at the advanced neural nets, CNNs, RNNs, some stuff about natural language processing like word embeddings. There's a holiday here If I'm not wrong, I checked the official calendar. I'm not very good at memorizing holidays, so I hope that's right. Then we have the transformers part and some transfer learning here. Second exam is roughly at the end of week 10 or beginning of week 11. So they are equally divided. And then we don't have exams anymore. The third part of the course is just generative AI. With the very end here, we're going to talk about, hopefully, if none of these things have to shift or we end up spending more time than planned, I hope to finish with multimodal learning, which is using not only one single modality, for example, not only images, but how to learn with images and text together, or image, text, and audio, how to combine all this kind of inputs to perform a task. And at the very last week is going to be just final project presentations. I didn't mention before, but I was planning for the exams. So for those of you who are in grad school, master's or PhD, the work is going to be individual. But if you are in undergrad, then you can work in pairs. Okay. That's because, well, reading a paper is going to be probably a new experience, and hopefully that's going to make it a little bit easier for you to do that. Because also normally you guys have more courses to take as well. And the distribution of assignments is there on the last column. At the very end here, it's all project implementation. And so I forgot to put it here, but somewhere here, you guys are going to have to submit the paper that you be reproducing. Right? So it's just, so you can start thinking about this paper already. And then at the week 5, you're going to have to just send the paper to me so I can check if it's good enough or if it's on the scope, if it's too hard, too easy, or whatever. Okay. Any questions?
Professor, what do you mean by evaluate the paper? Like, we're going to train the network or just load the weights and use?
No, you're going to have to re-implement. You're going to have to actually write all the code that trains a neural network, then train it from the scratch and evaluate it.
But if it was like a big network that we don't have the resource.
Yeah, that's why I need to read the paper before, because if it's like, if you claim, or if you try to reproduce, let's say, GPT-3, it's kind of be possible. We can reduce if you reduce the scope and reduce the model, you can train the same model but much smaller, right? So you won't be actually reproducing exactly the same thing, but you're going to be close to that. So we can discuss this a little bit further later.
It can be like just a fine tune, like pick already trained model.
Yes and no, because if you're fine-tuning, then there is probably code available. I want you to actually code the model from scratch. I want you to actually write the functions and the classes and everything. So if you can do that and pre-train the model, or if they give you the weights that fit on your implementation, then yes. But I'm actually more inclined to have something smaller that you can understand than something crazy big that might have a really cool performance, at least on the papers, but we can't understand or can't reproduce. Because the idea of the course is actually to understand how these things work, not to make them run. I don't want you to make something run and get a nice output but don't understand how it works. Okay, so by implementing from scratch, I hope it's going to make it easier for you to understand how these things work. Is it clear?
Yeah, I understand. Like, I can like pick 1 billion parameter model and load in my class and just continues to train like in a specific class, like test to SQL?
Yes, yes. If you code it yourself, you can use it, and the weights will work.
Okay, thank you.
If they were actually trained with the same architecture, they will work, but the code has to be new, not previous code. Okay. In terms of communication, I normally use Google Spaces. I'm not a WhatsApp person, so I'm very bad at responding and that. And I'm going to create a Google Space, which all of you should be already, it should be accessible for all of you because you have a UFV email. So I'm just going to make a Google Space there and add all of you automatically. And that's going to work as our major communication group. Feel free to create a private WhatsApp group without me if you want. But this is a space that I'm in, and I can ask questions very quickly. I can help with implementation. You'll be able to share code, and I think it's much better for that, right? This is much better for sharing actually ideas, papers, links, and all of like cool content you can find. And for example, if I'm going to be late for a class, I'm going to post it there. Oh, I'm running late, and someone please can just let the others know. So this is my like direct communications channel with you, and you can expect some sort of like 30 minutes latency. I have Google, like I use just the Google app on my phone, so I can answer very quickly, but just expect this response time. Email also obviously is fine, but because I get too many emails, I prefer to talk on Google Spaces because I know that space is actually for the course. So it's easier for me to go there and check all the questions and say, okay, this is that, and I can answer. And if I answer to someone has a similar question, it makes it fast for everyone. But feel free to drop me an email anytime you want, especially if you want to talk about personal matters. You have to travel, or there is a problem if you're grading, or anything that you don't want to share with the others. Okay, so then just email me anytime. Appointments. I used to have office hours, which was a dedicated time for attending students. But in practice, people either don't go or they don't use their time because they're busy, so they end up just making appointments with me anyway. So I decided to drop that and just have appointments on demand. So if you need to talk to me in person, just find me somewhere, just email me, direct message me, or just talk to me after class. And we can schedule an appointment to talk about anything you want. Wow, my computer is dying. Wait. I forgot my charger then. Wait, let me see how much time I have. Ooh, 10%. Okay, guys, I thought my computer would survive the whole lecture, but apparently it won't. I'll try to rush here, but if I drop, it's because my battery died. And then, yeah, I don't know what to do. I could go to my office and finish the lecture there, but then you all here have to have access to computers, because unless somebody has a MacBook charger. Okay, my bad. Okay, let's try. So there's a course website, okay? I don't use Moodle. Everything you need is going to be in this website. And the URL is this, if you want to take a picture or something. But I'm going to post also on the Google Spaces that I'm going to create right after the lecture. And yeah, so any announcements, anything that is important, I'm going to put there. The schedule, links to slides, to these recordings here. Everything is going to be there. Okay. Let's try to get started. We have 20 minutes left. I'm not sure my computer is going to support that. But before I actually get started, any questions about logistics?
So the lessons will be recorded?
Yes, I record the lectures. Feel free to watch them anytime. But if you need to miss the class here, and if you are enrolled here, not in Florestal, attendance is going to only work in person. So if you have to sign the attendance sheet to be considered, to have your attendance considered, and I'm going to consider that at the end of the course as well as part of like passing or failing.